Most of us would agree that graph analysis is one of the most common question types in the GAMSAT. Unfortunately, they're also really hard. Now, if you're one of these people who struggle with graph analysis, just know that you're not alone, and it's actually one of the most common reasons that people approach me for help. However, I do think that if you have a basic approach, just following a few core principles, you can actually find that that applies to a lot of different graph questions, and you can make progress really quickly. So today I'm going to share with you my approach to graph analysis and hopefully show you that you can conquer these questions just by following those basic principles. If you're new here, my name's James and I make content aimed at developing the skills and problem solving approaches that you need to do well at the GAMSAT, particularly section 3. In my opinion, that's the most important thing, yet a lot of the resources out there are aimed at developing more scientific knowledge rather than those problem-solving skills that I mentioned before. So I want to address that and actually make resources that do develop the things that you need to do well on the exam. And I want to do that without costing you thousands of dollars. So I make a lot of free content on YouTube, but I've also started making some paid resources such as a practice exam, which is actually what we're going to be going through today. So if you're interested in that, I'll leave it in the description, but please don't feel obliged to do so. Okay, so here we have questions 18 to 23 from my practice exam. And I hope that this looks a little bit like a graph analysis question in the GAMSAT. So what I tried to do when I modeled this one was a big confusing stem that explains the graphs, and then a couple of graphs that can be related by certain variables. So when you're looking at graphs in the GAMSAT, I think it's really important to think what you're going to be doing. So usually you're going to be getting one of the y variables, but you might need to get that in a few different ways. And the y variables are always this vertical axis. And a good way to remember that is just the y has kind of vertical component in the letter. And then the other axis, so the one going across, is called the x-axis. And that's because an x is a cross. And if you spell out a cross, it's a cross. Okay, so that's how you can remember the axes if you get confused. So generally, if you just have a rough idea that we're going to need to get the y variable from one or more of the x variables. Okay, so that's just your general approach. Now, for this reason, I think it's really helpful just to have a good, just general look at the graph and just see what it's actually showing you. So if we look at this first graph on the left, we can see that we've got volume. I'll just zoom in a little bit. We've got volume on the y-axis and we've got time on the x-axis, okay? And if we go across to the second figure, we can see that we've got flow on the y-axis and volume on the x-axis, okay? So good idea just to get a rough idea of what variables you're dealing with, and that shouldn't take you too long just to go through and find those variables. Now, with any question, I really recommend skipping the stem and going straight to the question. Now, the reason I say that is that the stem is usually very difficult, a lot of different words, things are relating to each other, and it's very confusing. So I think the stem is really good at answering questions, but not really just to read it and understand it. So, for example, if I asked you the question, what's FVC? You'll instantly be scanning for FVC. You'll find it here, and then you'll find that, and you'll be able to see that it's the total volume of air exhaled. So it's very good for that because you can find that in 1 or 2 seconds. But I think if you did it the other way around and you read through that stem and I asked you what's FVC, I don't think you'd be able to tell me. So that just kind of proves, that should hopefully prove to you that it's not useful reading the stem, because even when you have read it and you need to define something, you haven't actually learnt it in enough detail to define what it is, and you're going to have to go back anyway. So let's just cut out the middleman and just go straight to the question. So let's start with question 18. So as I said, we're generally going to be getting a y variable from the x variable. So if we kind of just define what we need to get the volume. How much air? That's how much of it, that's the volume of air, and we need it per breath. So we should already be thinking we need the graph where volume is on the y-axis, because you generally go from the x to the y. I guess you might be able to have some circumstances where you could go from y to x, but generally you're going to be going from x to y. So we should already be thinking, okay, well, this is going to be this graph on the left because this one has volume as our y-axis, okay? Now, we need to just understand this per breath. So this is a good example of when you can ask yourself a question and answer it using the stem. So maybe your question is, do these little oscillations in the graph, do they refer to per breath? Because ultimately, if they're not per breath, then maybe I've misinterpreted it and maybe I need a different graph. So we can go to the stem and we're basically just looking for evidence that those little oscillations are going to be an actual breath. So we can see here that they describe the process and it says the individual breathes normally for a series of breaths before a maximal inspiration. So it's very common to need to associate text interpretation with graph interpretation. So we can see here, okay, they breathe normally for a series of breaths and then they do a maximal inspiration and fill the lungs completely as possible, and then they exhale forcefully. And we can kind of see that now that we've got that context from the stem, we've asked a question of the stem, we've figured out the process, it makes a lot of sense when we start looking at this graph because we say, okay, well, they breathe in, that makes sense because the volume goes up. So again, just periodically checking with yourself to make sure that it's making sense. Then they breathe out, volume goes down. Okay, so that's the normal breathing. Then what's the next thing it says? A maximal inspiration, filling the lungs as completely as possible. Okay, perfect. So that's what that refers to. And then exhaling forcefully. So we don't need to understand absolutely everything about the graph immediately, and I wouldn't do that because a lot of the time they might give you two graphs or they might give you two graphs in a table, but you don't always need to use all of them. So I wouldn't waste time trying to understand them beforehand, but when you do, I'll just get a general understanding about, this is what's going on in the graph and just understanding that. If you can't understand it, it's probably better just to skip that question and come back at the end. So we've understood the graph now. So if we go back to our question, we're very sure that that left graph is what we want to use. And it says how much air is transferred per breath. So we said that these little oscillations are per breath, and we can see that we go from 2.4 to 2.9, and that's in liters. Okay, so very important that we always check the units. And that's something that you'll see as a constant theme. I'm always checking the units to make sure there's no mismatch. But you can see that we've got 0.5 there. So this would be A, because we've got 2.9 litres going back and forth between 2.4 and 2.9. So we're transferring 500 mils of oxygen per breath, or air, sorry. If you're enjoying this video, I'd really appreciate it if you could like, comment, and subscribe. It really helps me grow the channel, and I'd appreciate it a lot. Okay, so moving on to the next question. Question 19, what's the total capacity of the lung? So again, I think a really important part of every question is defining what it's saying. So total capacity, again, we're looking for the volume of the lungs, and that should hopefully draw you towards this first graph that we were looking at before. Now, in this case, we actually need the total capacity of the lungs. And this is where, you could rush in and you could say anything really. So I think the two numbers that would kind of be coming to your mind is either saying 6, because that's where we get up to, or saying 4.8, because 4.8 is the difference between the maximum and the minimum where we get to. So again, this is just a really important thing. Ask questions of the stem to verify your understanding. So we need to basically say, is it 6 or is it 1 or 4.8, which is the difference between the two? Basically, we're saying, what the hell does this mean? So if we go back to the stem and we ask ourselves that question, they exhale as much as possible until no further air can be expelled. However, the lungs are never completely emptied. So what this little volume down here represents is the volume left over. I would think it's fair to assume that. So this is, a lot of the time you're going to need to infer things from the information that they've given you, but I think it's very fair to assume that that's the volume left over. So I would say that the total lung capacity is going to be 6 litres, because that's the maximum that we can get to. And yes, we can breathe out a maximum of 4.8, but that's not what the question's asking. It's saying what's the total capacity of the lungs. So we need to make sure we include this little volume left over here. So that would be C. Question 20 now. Based on the testing procedure described, which direction would the flow volume curve be produced? So this is, you can just feel, this is what I'm saying by really describing what the question's asking. You can feel from that it's clearly different. It's not asking for the volume. Now it's asking for the volume, the flow volume curve. So it directs you straight to the graph that we need. And what we need to actually figure out is the direction that it would be produced. So what's that meaning? So it's basically saying, where's the start point? Where's the end point? So again, to do that, we're going to need to do a little bit of text interpretation. And you can see that I'm just going to skip over all this. I haven't read any of that. And, you will be seeing this question for the first time, but hopefully you can see that of everything that I've highlighted is the information that I've needed at the time. And I don't really need to understand those things yet. And I don't need to understand them for this question. So if I had have spent a lot of time there, I'm just wasting time and just adding more stuff to my brain, increasing the likelihood that I'm going to get confused. So what I would more be focused on is this part here, because it can also measure flow. So the procedure is similar, but the recording is only performed for one forceful breathing cycle. So they inhale as much as they can, exhaling that breath as fast as possible to produce a flow volume curve. So if we kind of infer from that this graph here actually refers to this portion here. That will be exactly the same thing, because that's a forceful inspiration and exhalation. So we need to think, well, what would be happening here? So it starts with when they inhale as much as they can. So what would be happening there? Well, we would have empty lungs because we're inhaling. So we would have to start here at point D, and then we inhale, which increases the volume of our lungs. So we could either go this way or this way. So these are the two directions that we can get to that point here, but it's a little bit tricky to figure out which way we go. And what I wanted to get across with this question is that there's multiple ways to do it. So you could look at these flows numbers. So if we think about it, the machine is measuring the flow. So if you're inhaling, there should be a negative flow out of the machine. So that would imply this. But at the same time, you could probably make an argument that that might be positive flow, because maybe it's measuring the flow, going into your mouth or something. So it's a little bit, that is one thing that you could use, and you can maybe infer it from there. But the other thing that you can use here is actually the slope of these graphs. So you can see that this part, it's very fast, and then it's really slow. And then in this bottom graph, if we took the bottom line, it's kind of a more constant graph. And I just think, what happens when you inhale? So if you inhale, like really as much as you can, it's kind of a gradual process. But then if you forcefully exhale, like what the procedure told us to, you're going to go really fast and then do a little bit at the end. So there's a few different ways that you could get that information. But this bottom section here would be the inhalation, and this top part would be the exhalation. So if we're looking at the question, which direction would the flow volume curve be produced? It would start at the rightmost point on the x-axis, right? Because that's the rightmost point over here. And then it would proceed counterclockwise going this way. So this one would be D, because we would start here. I'll rub out everything on the graph because it's getting a little bit messy now. So we'd start here when the lungs are empty, we inhale, 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 and that's quite a constant process, so that's how I know I'm going that way. Our lungs are now full, and then we forcefully exhale, which is here, and then the volume kind of gradually drops back down to zero that way. If you wanted to have a go at this question and more, the full-length practice exam is available on my website, so I'll leave the link in the description if you're interested in that. Okay, question 21. So point C on the flow volume graph refers to which point on the volume time graph? So this is a really common skill that I see, and it's basically trying to relate two graphs to each other. So if we think about it, we need to find a point C, which is here, on our volume time graph, which we generated before. Okay, so you can see that it's a bit tricky because you're like, well, what do you mean? How do I get this point? What is that on this graph? And this is kind of that relationship between graphs that I see. And I think the easiest way to do this is to find what I call a shared variable. So if you remember before, I said that this one has volume and time, and this one has flow and volume. So you can see that both of these, oops, not time, they both have volume in them. So it actually means that we can relate certain points based on that shared value. So for example, if we get this point here, so when the lungs are full, that has to be this point here. And when the lungs are kind of more empty at 1 point, whatever, 2-ish, we know that it's this point here. So we can relate different points because, how do I know that? Because these both have 1.2 as their volume. Right? They both have 6 as their volume. So if you can find a variable that's shared between graphs, then you can actually relate them based on that shared variable. So in this question, we need to relate point C here to our volume time graph. Now we know that it's somewhere near where the lungs are getting full, and we know that we inspire this way. So this is our inspiration. And then we also know on our volume time graph that this is our inspiration. And this point C is near the top of inspiration. So it'd be somewhere around here would be point C. So it's about just kind of relating different areas of the graph based on the shared variables that we have. So that's how I know that. It's because it's about 5.8 or something. So, you know, that's roughly 5.8. So, yeah, it's all about just finding that variable that's shared across the graphs, and it allows you to relate them. So point C would be where? So is it the segment where the individual's performing a forceful exhalation? No, we know it's inspiration. Approximately when the lungs are at their maximum capacity, that looks pretty good. The expiratory phase of normal regular breathing, no, that would be this portion here. So it's not that one. And the inspiratory segment ascending from 2.9 litres to 4.8, which is not quite it, because that would be going from kind of here to here, which would be, if I, just to kind of prove my point, we could map that from 2.9 on this volume axis to 4.8. So it'd basically be that segment there. So if I highlight that in green, that segment is the same as that segment. Okay, but we want point C, which is after that. So it's closer to when the lungs are at their maximum capacity. So this one would be answer B. All right, so moving on to question 22. So which letter labeled in the figure represents the FEV1? So again, we're going to need to relate different portions of the graph. So A, B, C, or D. Now, again, we can just find, now that we know what we need to find, we can ask the question of the stem. So it's going to get a little bit like a rainbow, but you know, if you're looking for FEV1, you very quickly get drawn here, which indicates the volume expelled in the first second of the forceful exhalation. So I'm just going to have to kind of go back a little bit, but they're talking about the forceful exhalation beforehand, and then the FEV refers to the amount expelled in that first second of the forceful exhalation. So again, you know, it's very easy to find that information if you're looking for it But if you had a read through, you probably wouldn't have determined that. So again, we're just going to be going to our graphs, and we know that we could use either graph actually, because we know that this is the forceful exhalation, but we probably care more about this one because we do need to actually find the letter. So we know that this is the forceful exhalation phase, and if it's going to be the first second, it's going to be that first second there. So it's going to be A, the first portion of that graph. Okay, and last question, question 23. So what would be the effect of an obstructive lung disease on the flow volume loop? And it's talking about AB, CD, AC, BD segments. So it's all flattening. So it can be also good to just look through the options and see what you actually need to determine. So we basically need to see between which two segments, broadly speaking, this is going to be most combinations of the two segments. Between which two segments is there going to be a flattening in an obstructive lung disease? So again, we just go here and we find the information that we want. So I might rub out all the other stuff that we've done because it's getting a bit too colorful for my brain. So we're just looking for obstructive lung disease. So we can find it down here, which are characterized by an impaired ability to forcefully expire air. So we know that our forceful exhalation segment is this bit here, or at least it's kind of the whole thing, but you'd assume that that's probably going to be the main exhalation segment. So we're going to get a flattening of the A and B segment. So the AB segment is going to be that bit here. So what you're going to get is you're going to get a graph which is more like, I'll draw it in purple. So something like this. So you can see that whole segment, that whole part of the graph is the flow that we're getting, so the liters per second. So if we're struggling to forcefully expire air, we would expect that flow to be slower. So we can see that it doesn't get up as high. In our purple graph, it's 5, whereas in the original blue graph, it was 8. So there's a stronger flow there because we can get the air out. But in an obstructive lung disease like that, we're going to struggle to get the air out. So that's why that segment of the graph gets flattened, that AB segment. So the answer to this last question will be A.